This Zoom session is being brought to you by the Fractal Almond Octaves Z. All right. Today is the last section in the book that we are scheduled to cover. I have other things I'd like to cover after this, particularly in the extra credit, what did I call it again? The hourly trigonometry extra credit set. But aside from that, okay, this is a little bit about vector algebra. This has a marginal reference to trigonometry and mentions a sign, but other than that, it's just basically arithmetic. But we'll do it anyhow. Okay, cross product. This is V cross W, like here. It's strictly for three-dimensional vectors. It takes a 3D vector cross a 3D vector yields a 3D vector. That's pretty unique. Given the components V1, V2, V3, and W1, W2, W3, there are all these differences of products. They're basically determinants. V2, W3 minus V3, W2, V3, W1 minus V1, W3, V1, W2 minus V2, W1. If you use a 3x3 determinant, you can express this in terms of 3x3 determinants. Put an I, a J, and a K vector in the first row, V1, 2, 3 in the second row, W1, 2, 3 in the third row. And by the definition of determinant, this determinant equals this. It even takes care of the reversal for J, V3, W1 minus W1, V3, which is the reverse, but that's because of the what you might expect. But there's a negative in the expansion of a 3x3 determinant. Okay, so it's this. And it has these two rules. One is that the cross product, V cross W, is perpendicular to both V and W in three-dimensional space. The length of the cross product is the area of the parallelogram that V and W span. And therefore, the length of V cross W is length of V times length of W times sine of the angle theta between them. Sine rather than cosine, which is what you get for dot product. Now, there are various rules. It acts rather like an ordinary product, except for a few unusual things. For example, U cross U is always the zero vector. Any vector cross itself is zero. U cross V equals minus V cross U. So it's what's called anti-commutative. If you multiply this way, you get a vector pointing this way, whereas if you multiply in the other direction, get a vector pointing in the opposite direction. There's another point here. Yes. There's what's called the right-hand rule. If V is here and W is here, then you sweep like this, and your right-hand finger points along the cross product. So there has to be a handedness to it because of the nature of the cross product, and also that tells that connects with how you'd make these differences in this direction rather than the other. Okay, a number, a scalar times U cross V is alpha times U, that cross V. And U cross V dot plus W equals U cross V plus U dot W, cross W. So it's commutative, so it's distributed over vector addition. And scalar multiplication associates with it. However, U cross V cross W is not U cross V cross W. It's not associated. Things get a little wonky. So there's some examples. This is to remind us of what a determinant is. 3, 4, 1, 2. Its determinant is 3 times 2 minus 1 times 4, which is 6 minus 4, or 2. Now here we have a 3x3 determinant. Expanding along this row will be plus A times this minor, minus B times this minor, plus C times this minor. A times determinant 3, 5, 0, negative 2, minus B times, just a second, minus 1, 5, 5, negative 2. And plus C times 1, 3, 5, 0. So minus 6A plus 23B minus 15C. And if A, B, and C were vectors I, J, and K, then this would be this vector cross this vector. Now, okay, here we have some vectors, 2, negative 3, 1, 3, negative 2, negative 1. What's U cross V? What's V cross what's V cross W, what's W cross V, what's W cross W, and what's V cross V. Okay, the last two are easy. W cross W and V cross V are both the zero vector, as is the case for any vector cross itself. All right. V cross W and W cross V are opposites of each other. So all we really need to do is find V cross W. So for V cross W, put -2, -3, 1 in the second row, and 3, -2, -1 in the third row, and IJK in the first row. And expanding along the first row, it's I times vector -3, 1, -2, -1, minus J, because it's plus minus plus, and you expand a determinant, minus J times 2, 1, 3, -1, plus K times 2, -3, 3, -2. And after a little bit of work, it's -1, 5 by 5. And therefore, V cross W is the opposite of that, or 1, -5, -5. Now here we have a curiosity, a dot product with a cross product. Now this turns out in general to be the area, the volume of the parallelepiped spanned by these three vectors, but that's a detail for later. Let's work on this. 2, -3, 1 dot -3, -3, 2 cross 1, 1, 3. For this cross product, the first component is 3 times minus 3 times 3 minus 2 times 1 by 3 times -3 minus 1 times 2, -3 times 1 minus 3 times 1. And so after a bit of work, it's 7, 11 by -6 dot 2 by -3 by 1. And then to expand that, just a second. Expand that, 2, -3, 1 dot 7, 7, 11, -6, 2 times 7 plus -3 times 11 plus 1 times -6. After a bit of arithmetic, that's -2 by 5. -25, my apologies. Okay, that's it for now. Okay, let's conclude this.